Hello again. This is Math 2115 coming to you from the College of DuPage, and the title of this lecture is General Recursive Definitions and Structural Inductions. And as always, I encourage you to be an active learner while watching this video. Sequences of numbers are not the only objects that can be defined recursively. In this lecture, we discuss recursive definitions for sets and for functions. We also introduce the idea of structural induction, which is a version of mathematical induction that is used to prove properties of recursively defined sets. Let's begin with recursively defined sets. To define a set of objects recursively, you identify a few core objects that belong to the set, and then give roles to show how to build new set elements from the old. More formally, then, a recursive definition for a set consists of the following three components. There's a base, a statement that certain objects belong to the set; a recursion, a collection of rules indicating how to form new set objects from those already known to be in the set; and a restriction, a statement that no objects belong to the set other than those coming from either the base or the recursion. Let's give an example of this, and then we'll talk about a recursive definition of a Boolean expression. Now, we talked about this much earlier when we were talking about logic, but the set of Boolean expressions that are legal involve letters from the English alphabet, P, Q, R, and all of the others, and the symbol, conjunction, disjunction, negation, and parentheses. To make precise which expressions are legal, the set of Boolean expressions over a general alphabet is defined recursively. Base. Each symbol of the alphabet is a Boolean expression. And if P and Q are Boolean expressions, then the following are also Boolean expressions. So you can take the conjunction, the disjunction, the negation, or put something in parentheses, and it's still a Boolean expression. And then the restriction are, there are no Boolean expressions over the alphabet other than those that are defined by the base in this recursion step. So derive the fact, show that this in fact is a Boolean expression over the English alphabet, and those are the letters of the alphabet. Well, first of all, the letters are Boolean expressions, and by the properties we know that these two are also Boolean expressions. So what we can do is we can do conjunctions of two Boolean expressions to get a new Boolean expression, and then you can negate this one and that one, and then you can take the disjunction. So you see what you've done is you've gone through and you've shown that in fact this is a Boolean expression. Computer programs do this to validate syntax. Let's talk about recursive definition of parentheses structures. And here, for example, sometimes you'll be typing something and the computer will come back and tell you that you didn't have your matching parentheses. That's what we're really talking about. You have to have legal parentheses structure. And so here is a recursive definition that generates the set of legal parentheses structure. This is the way compilers are programmed to check this. So the base says that a parentheses like that is in the set of C, legal parentheses structures. And if E is in C, you can put E inside of parentheses, so you can nest parentheses. And you can also put parentheses next to each other. And the restriction is no parentheses structure are in P other than those obtained from the base and the recursion. So what we're supposed to do is we're supposed to show that this expression is a legal expression. This one. Well, certainly this is in C by the base and by the recursion relationship, and this, we know that you can put that parentheses inside another parentheses. But then by part 2b, you can put them next to each other, and that's also in C. So you see, recursion is used to give a formal definition for a set of all strings over a finite set as well. That's coming up next. So here is a recursive definition for all strings over a finite set. Let A be any finite set. Call the elements of A characters and define the set S of all strings over A as follows. And again, this is the recursive definition. We had a different definition before. So lambda is a string, and lambda is the null string, the string with no characters. But then the recursion step is new strings can be formed according to the following 3 rules. If U is any string in S and C is any character, then C is a string in S, where UC is the concatenation of U and C and is obtained by appending C to the right of U. Another way you can do the recursion is, if U is any string, then both the concatenation of lambda and U, denoted lambda U, and the concatenation of U and lambda, denoted U lambda, is equal to U. So we have this identity. And the third element of the recursion is, if U and V are any strings in S, and C is any character, you can append a character and there is. So you're appending the C on the right, and it's also, there's an associative law. And the recursion then, or the restriction for the recursion definition, is nothing in a string in S other than the objects obtained from the base and the recursion are in S. So we can have theorems that we can prove this way. So if A is a finite set, and S is a set of all strings over A, then every character in A is a string in S. Well, suppose C is any character in A. Then lambda is a string in S by our base assumption. So C lambda is a string in S, but C lambda is C, therefore C is a string in S. You can also use recursion to prove a property of strings. Suppose A is a finite set, S is a set of all strings over A, and A and B are in capital A. Because of the way the definition of string was stated, it cannot be deduced immediately that BAA is a string in S, but we can prove it true by a recursion, because first we show that BA and BAA are strings in S, and then use the fact that we have BAA with the parentheses like that is the same as BAA. Okay, so by our theorem, if A and B are strings, because both A and B are in A. And we know that BA is a string because B is in S, and we're appending the A to the right-hand side. But then we can take this being in the string, and we can append an A to the right-hand side. But we have this associative property, so that means that this is true. And by 3 and 4, BAA with parentheses there is a string because it equals BA in parentheses A, which is a string in S. You see, this is what you're doing to check that things are in fact valid from a syntax point of view. In a very famous book, Gödel, Escher, and Bach, Douglas Hofstadter introduced recursively defined strings of M's, I, and U's, which he called the MIU system. So the base was MI is in the MIU system, and if XI is in the MIU system, where X is a string, then XIU is in the MIU system. In other words, you can add U to any string that ends in I. And we have 2 others. If MX is in this system, where X is a string, then MXX is in the MIU system. In other words, you can repeat all the characters in a string that follow an initial M. For example, if MUI is in the system, then MUI can be followed by UI, because that is in the string. If XIIIY is in the MIU system, where X and Y are strings, possibly null, then XUY is also in the system. In other words, you can replace 3 I's by U and still have something in the system. And if XUUY is in the MIU system, where X and Y are strings, possibly null, then XUY is also in the MIU system. In other words, you can replace UU by U. And the restriction is no strings other than those that can be derived from those 1, 2, including all these parts, are in the MIU system. So show that MU, IU is in the MIU system. Well, MI is in the MIU system by 1. That's the given. And by 1 and 2b, we know that that MII is also in the MIU system. And we can apply that again to conclude that this is in the system, but then we can replace some of those i's with u's to get this, and then by 4, which is this step, and by 2a up here, MU, IU is in the MIU system. Again, it doesn't seem very exciting, but that's how we check syntax with your computer programs. We'll talk about more of these things, but now more than ever, time is precious. Each day must count. Do the math. It'll make you strong. And now more than ever, take care of yourself and of each other. We'll talk not in quite such abstract terms, but we'll have other examples that will come up in the continuation of this lecture.